we are also happy to note that he will sort of do experiments related to some of our theories, and also hopefully we'll get some ideas from some of his works and so on. And I was also happy to note that some of our experimentalists have had fruitful interactions with him, and notably our students. So without much ado, I would like to request our director to formally introduce him.
Professor Ramesh, distinguished speaker of the 12th Jessivas Metallurgy from Indian Institute of Science and a PhD from the University of California, Berkeley in 1987. He returned to Berkeley in 2004 and is currently the Purnendu Chatterjee Chair Professor in Material Science and Physics. From 1989 to 1995, at Belcore, he initiated research in several key areas of oxide electronics, including ferroelectric, non-volatile memories. His landmark contributions in ferroelectrics came through the recognition that conducting oxide electrodes are the solution to the problem of polarization fatigue, which for 30 years remained an enigma and unsolved problem. In 1994, in collaboration with S-Gene Lucent Technology, he initiated research into manganite thin films, and they coined the term colossal magnetoresistive CMR oxides. He initiated a pioneering research into multiferroic oxides in Maryland. At Berkeley, he continues to pursue key scientific and technological problems in complex multifunctional oxide thin films, nanostructures, and heterostructures. His group demonstrated the existence of a large ferroelectric polarization in multiferroic films in agreement with first principle predictions. They also demonstrated electric field control of antiferromagnetism as well as ferromagnetism, a critical step towards the next generation of ultra-low power storage and spintronics devices that are completely electric field controlled. He has published extensively on the synthesis and materials physics of complex oxide materials, and his work is highly cited. More than 600 papers with over 65,000 citations. He is a fellow of APS, AAAS, and MRS. He has been recognized with a Humboldt Senior Scientific Prize, the American Physical Society David Adler Lectureship, and the James McGody Prize, and the TMS Burden Prize. In 2014, he was recognized as a Thomson-Reuters Citation Laureate in Physics for his work on multiferroics. From December 2010 to August 2012, he served as the founding director of the Sunshot Initiative at the US Department of Energy, overseeing and coordinating the R&D activities and funding of the USA Solar Program. In 2011, he was elected to the National Academy of Engineers. He is currently the Associate Laboratory Director of Energy Technology at the Lawrence Berkeley National Laboratory. With this short introduction, I now invite Professor Ramamurthy Ramesh to deliver 12th Jessivas Memorial Lecture on Electric Field Control of Magnetism. Professor Ramesh.
Thank you, Professor Mohanty. Thank you very much. It's a pleasure to be here. We were talking. We have to mic up before we talk.
On.
Good. Yeah. Can you guys hear me at the back? Good. All right. So if I speak very fast, it's just jet lag. I'm trying desperately to keep awake. But you know, we were talking about this at lunch today. You know, this institute, Professor Saha, or Professor Bose, or the other Bose, Satyendranath Bose, these guys are amazing scientists. You know, and we want to put more and more emphasis on science. I have to tell you, I'm a big science wonk. Professor Mohanty was talking about the Sunshot Initiative. It was a very crazy, bold initiative. But the biggest thing for me was I worked with Steve Chu, Nobel laureate, amazing guy, deep convictions about science. And I'm hoping that some of that will get conveyed today as well. It's important for India, for sure. Science is a great pathway to better the nation, science, technology in a broad sense. Okay. So that will be part of the background for the discussion today. What I wanted to try to do is to give you a flavor for some of the work that we've been doing. You guys are all physicists, and so you understand that these two are different quantum mechanical quantities, electric field, magnetic fields. The question is, how does one manipulate one with the other? Okay, that's kind of the ethos. What I want to try to do today is to give you a picture from about 100,000 feet, which really means take you back to economics and say, why am I even thinking about this? Outside of the physics, which is really fascinating, but why do I want to do this? And slowly go from 100,000 feet all the way down to Earth and say, how does one go about solving the problems? Okay, acknowledge a lot of people. We work collaboratively because the problems are so difficult. It's very difficult for one person to solve it by themselves. So we work with a lot of people. Let me point out some people. The group from Intel has been amazing. This fellow, Sashi Manipatruni, is an Indian fellow, amazingly smart guy. And I wish I was as smart as this guy. He knows so much about so many things, and he's only 32 years old. So for me, it's like, the last hurrah or something like that. But it's been a lot of fun for the last 2 years. I work a lot with this guy, Darryl Shlom. He's an MBE guy, and we will see some results from him as well. And you can see a whole bunch of other people. Nicola Spalding, ab initio theorist. Some of you know her very well. This guy is a really good theorist. He's in Luxembourg, that's LUST. Several of my former students and postdocs, I still continue to work with them because it's so much fun to be able to argue and debate and stuff. Of course, like you all, we are funded by various agencies and we acknowledge them. Very thankful for their support. So this is the 100,000 foot picture. So we have to pause and say, what is going on in the outside world? If you look at it, microelectronics, everybody has a cell phone, everybody has a laptop, et cetera, right? If you look at it in terms of the business, how big is that market globally? People always believe that's a $300, $350 billion market. And you say, what is happening over the last 5, 10 years that might change it? And one of the things that's happening, how many of you have not heard of the term IoT? Internet of Things. Awesome, that's great, everybody, yeah. So we'll give you a quick 15-second primer on IoT. You can think of a building like this, right? You may have 1 million sensors. It can have people sensors, pressure, temperature, every variable you can think of, so that you can automate it. And so this picture is basically showing you how macro scale systems, whether it's the transportation system or the built environment or the electricity system, all of these things can be connected to each other. They're all connected by, of course, the usual things. They have communication devices. Many of them are semiconductor devices. You have information storage. All of these are happening. So going forward, for example, I make this kind of casual remark, but it's serious. If you wanted to stop somebody's car, you could do that. One way to do it is put a cow in front of the car. But the other way is actually send a signal which will turn off all the electronics in the car. And therefore, this whole network, this whole thing here, a huge macro system, is kind of the underpinning for the Internet of Things. So one of the consequences of that is that this market, which used to be $300, $350 billion, is growing significantly. Okay. And that's what is shown here in this slide. It's showing you that the market size can be about $400 billion end of last year, and it's projected to grow to maybe, let's say, $1 trillion, 10, 15% growth annually. Okay. Now, all of these, most of these actually, are underpinned by silicon. And that's the bread and butter of all of these technologies. And you all know that Moore's law, transistors, has been the underpinning for the last 60 years, since the inception of the transistor. Let's say from the early 60s, it's been the backbone. Everybody now knows that Moore's law is not tenable anymore because you're now getting to dimensions which are of the atomic scale, not necessarily about the order of a few nanometers. There are some fundamental limits to this techno-economic law that you say, I have a problem, which is why Intel is now deep into it. Samsung is deep into it. TSMC is deep into it to discover pathways to do logic in a different way. Okay. Now let's look at this whole question from one particular perspective, okay, which has to do with energy consumption. Okay. If I look at this red curve, if I did nothing to today's CMOS or Moore's law, where power consumption is about 100 picojoules. People will argue maybe it's 30 or 50 picojoules, order of picojoules per logic operation. Okay. If I don't do anything but IoT is continuously taking off, or some kind of an exponential takeoff, then by 2030, I could have up to 20% of primary energy, okay, which means that's the coal that you burn and you convert to electricity. That efficiency process is about 35% efficient. Okay. So today, it is about 4% of primary energy, and nobody really cares. But worldwide, if this takes off, you could be talking about 20% or so of primary energy. That then becomes a big issue. To calibrate all of this, at least for the United States, transportation, basically burning fuel in your car, is about 24%. Buildings in the US consume about 38% of primary energy. Manufacturing, paper, glass, all those manufacturing processes consume about 20 to 25%. So it gives you a calibration of what can happen to the energy consumption in these electronics if you do nothing to it. Okay. So I'm going to now show you two other scenarios. One is what I call the moderate scenario. If I go from, say, 100 picojoules and reduce by a factor of 5, and we think we can get down to something here, which is not a great scenario, but we will take it. One pathway, and I'll show you an example of some really beautiful work that's happening at Berkeley, is to use negative capacitance in ferroelectrics. Now, I could say, is there a possibility that I have a totally new Moore's law? In this case, we're talking about 20 femtojoules, 3 orders of magnitude reduction in the power consumption per logic operation. If that happens, I could kind of keep my energy consumption to approximately where it is today, maybe 6 to 8% total primary energy. Okay. So that gives you a backbone for why one would need to think about this kind of a problem. Now you can go back to somebody like Intel and say, hey, what are the possible pathways? I'm going to focus on one of them in my presentation. One could start to think about this whole game by saying, I want to go from somewhere in the 100,000 KT, which is approximately where we are, KT is room temperature, down all the way to the Landauer switch, which is the adiabatic process, which is KT log 2. Getting to KT log 2 is going to take us some time. But even if I can get to 1,000 KT or 500 KT, there's huge room for innovation, huge room for big changes in energy consumption. The other pathway is to say, look, let's not do Boolean computing. Let's not do binary-based computing, but do stochastic computing. Okay? And that's what is shown here, which means I can start to look at probabilistic type approaches, more computational oriented. And the third part, which the folks in Intel are pushing all of these, is to go from, again, using this Boolean type logic operation to a neuromorphic type computing, which IBM has been pushing for quite a while now. And this is a very viable pathway as well. So in my talk today, I'm going to focus primarily on this part. Okay. We meaning Intel, myself, we all believe that there's a fundamental transition that needs to happen. And I have to tell you, to me, the stunning part in all of this is that it did not come from a physics professor like me. It actually came from Intel. These are hardcore EE people who believe in CMOS. And they're telling us we need a transition from the way the electron works in silicon to something different. And that's captured here. If there's one slide that is really important in this talk, perhaps this is the one. Okay. Let me take you through this carefully. That is the standard MOSFET, nothing dramatic. Okay. It is governed by a Boltzmann equation, which you can see here. That just tells you how the state goes as a function of the energy. Okay. I can use this, and then I can calculate something which the EE people will live and die by, which is simply how does the IDVG look like. Okay. And if you look at that blue curve there is the curve, which is the manifestation of this stuff. This basically maps into the fact that the current I is proportional to the exponent of the Q times Vg by kT. And you can see for a decade change in the current, the voltage basically changes by 60 millivolts. That 60 millivolts per decade is called the Boltzmann tyranny, because you cannot break it for an electron. Okay. That's an important number to keep in mind, because you're going to say, imagine I could use a metal insulator transition. Imagine something which did not have a 60 millivolt slope, but which went straight up. What can I do with that? And you all are working quite a bit on this. I've talked to people this morning about this stuff. So this is a curve. This is actually a review of a paper that one of my colleagues, Saif Salahuddin, amazingly smart guy, a few years ago, maybe 10 years ago, he proposed using a ferroelectric in series with a MOSFET to create something called negative capacitance. And by using a negative capacitance, you can reduce the slope from 60 to 50. By simply going down by 10 millivolts, you can gain 3 orders of magnitude or so in energy reduction. So it's very important that the slope becomes as small as you can. So going from this Boltzmann statistics-based approach to something where interactions are important is a big leap of faith for a company like Intel. It's a big leap of faith of all of electronics. Okay? So now you say, what are the pathways? One pathway is simply to use a ferromagnet. And in a ferromagnet, we know that you have exchange interactions. It's how these electrons or the spins talk to each other. So instead of looking at each electron separately, is there a way that I can start to look at collective behavior? It doesn't have to be a spin. It could be a dipole moment in a ferroelectric. It could be correlated electrons in manganites, for example. So the fundamental premise is this time for us to walk away from very standard Boltzmann type distribution into something that has a lot more interaction, a lot more correlations? That's an important question that we're beginning to ask. That brings me to, I'm going to just show you a couple of slides to tell you what we do. We are material synthesis people. My group does a lot of synthesis, and we work on a few material systems or problems. Today we're going to talk about magnetoelectric effects, why that is important. We're going to tell you in a few minutes. Electric field control of magnetism, obviously. We used to, when Arun Majumdar used to be at Berkeley, now he's at Stanford, we used to do a lot of phonon physics. There is a very interesting question in phonon physics, has to do with localization of phonons. Nobody's figured out a way to do it. So he and I have been kind of going back and forth. We did some work where we thought we saw phonon localization, not really sure. We look quite a bit on emergent phenomena. That's a topic of discussion tomorrow at the other Bose Institute. And we do look at, in these pyrochlores and perovskite type systems with large spin orbit coupling. So we look at topological phases, but looking at them in thin film form. Those are the material systems that we look at. How do we do what we do? We use epitaxy as a pathway. I was so excited to see all of the single crystal capability that you all have here. We make single crystals in a slightly different way. We grow it one atom at a time by MBE-like processes. We're also poor people, and therefore we use a laser MBE process rather than a gas source $3 billion MBE system. We use a $300,000 laser MBE system. We collaborate extensively with theorists. If there's one thing that has been, for me personally, the biggest learning is working with theorists. It's just amazing what theorists can do today. I remember the first time, we're going to talk about bismuth ferrite in about 5 minutes. The first time we talked about all of these correlations and stuff like that, we had a 7-hour argument. We started about 8 o'clock or so at night at the MRS meeting. We went on 8 plus 7, whatever, 3 o'clock, 4 o'clock in the morning, arguing about it because we didn't understand what the theory guys were saying. Today, correlations are so important in our discussion. So we cannot, as experimentalists, we absolutely cannot do anything without the participation of theorists. Okay, so here's a big shout out to all the theorists in the audience. We do quite a bit of imaging. Now, I'm a microscopist by design. We have some fantastic capabilities at Berkeley. We have perhaps the highest resolution electron microscope, half an angstrom resolution, and we have a whole bunch of other capabilities. We have perhaps one of the best soft X-ray sources in the world. at the ALS, where we do quite a bit of spectroscopic work, and you will see some data today. And we work with our EE colleagues and looking at some device physics. That's kind of the how we do what we do. I want to spend 2 minutes, and these are perhaps important slides. This is going to be a precursor to ask the question, hey, why am I even trying to control magnetism with an electric field? Should I not be using a magnetic field instead? Okay. So here's an example for those of you who work on manganites, colossal magnetoresistive materials. That is the MR. This is for lanthanum calcium manganese oxide. And it basically shows you that you have, huge 70, 80, 90% change in the resistance of the material with the magnetic field of about 6 Tesla. Okay. At the bottom, you have the parallel universe of colossal electroresistance, where the resistance changes by about 60%, with a field of about 400 kilovolts per centimeter. Okay. Now I'm going to pause there and take you to the right side and simply take you to a textbook and say, if I have to generate a field of 6 Tesla for a physicist, that's 8 Kelvin. You say, it's a very low energy scale. No big deal. If you're an engineer, you say, oh my God, I lost my business. I'll tell you why that happens. If I have a wire, you can use Ampere's law, or Biot-Savart's law, and calculate the magnetic field. For a 6 Tesla magnetic field at a distance of a micron from this wire, you need a current of the order of amps. Whether it's 30 or 25 is really not a big deal. It's of the order of amps. Okay. And for that kind of a current, you need a big battery which is pumping it through. Okay. And therefore, you have an immediate problem, which is a matter of energy consumption. To create a field of 6 to 8 Tesla, you need to have a lot of energy pumped into the system. This is one reason why CMR never worked as a technology, because the fundamental energy scales for that system did not match up. Okay. At the bottom, I'm giving you the other quantum mechanical quantity, the electric field, which scales with the dimensions of the object. So if I had to get a field of 400 kilovolts per centimeter for a 1 millimeter type object, which is here, I need 40,000 volts, which is shocking, which is a very large voltage. On the other hand, if it's a 100 nanometer thick sample, or even better, a 10 nanometer or 1 nanometer thick sample, that voltage is going to progressively decrease. So if I'm going to be using nanostructures, very, very small structures, I'm perhaps better off using electric field as my way to manipulate and change. Then the question comes, can I actually manipulate magnetism with an electric field? Okay. This is a slide that my colleague at Intel, Sashi, he and I will put it together. It's kind of a provocative slide, and I want to take you very quickly through this. Oh, not this one. Okay. On the left side, this is what the spin transport people will talk about. It's basically, on the right side, it's current-driven spin-torque switching, so which means you have a current, and you apply a spin torque to it, and you can move domain walls. So this is the basis for the STT RAM, for example. But the key point in all of this is, and this was kind of typically we chat about 9 o'clock to 10 o'clock every night. We argue about various things back and forth. This hit us in the face. It said, if I have 1 electron, it basically gives you 1 Bohr magneton. Okay? So if I needed to have a large amount of spin torque, I need a large number of electrons, a large current. Okay? On the other side, if I have a magnetoelectric type switching, my energy goes as half CV squared approximately. I can get to an attojoule very easily. We're going to get to the attojoule question in a second. But each electron can generate a field of, it's just this equation. Therefore, you can actually generate quite sizable electric fields. So the argument, it's kind of a fuzzy argument, is that, hey, if I can somehow use electric fields as my knob, I'm perhaps better off using that rather than a magnetic field. Okay, that brings me to multiferroics and says that's the pathway by which we're going to try to do this crazy experiment. So these are materials, and here's the description of order parameters. Ferromagnetism breaks time symmetry. It's got a spontaneous magnetic moment. Ferroelasticity is martensite, for example. It neither breaks time symmetry nor spatial inversion symmetry. A ferroelectric or a piezoelectric breaks spatial inversion symmetry, but it doesn't break time symmetry. Ferrotoroidic materials break both. And bismuth ferrite is one of them. We're going to talk about it. So you could have the synthesis of these two orders in a material which has a spontaneous toroidal movements. In tomorrow's talk, we will talk extensively about creating toroidal type movements in some vortex structures. Okay. And this gives you the thermodynamics of the system, the coupling between the conjugate variables, electric field polarization, magnetic field magnetization, stress strain. They're all the conjugates in Gibbsian language. What we are looking for are the cross-coupling between magnetic field and polarization, or electric field and magnetization. Okay, a quick description of how you can atomically design these kinds of systems. I'm going to focus on this guy and a little bit of this at the end of my talk. So you can now start to say, if I need to have a material which has both magnetic order and electric order, which means I have a spin degree of freedom which has got an order parameter, I have a charge degree of freedom which has an order parameter, and if those two things are coupled to each other, it is a magnetoelectric material, and bismuth ferrite is one of them. Okay. So I could design them by taking the A site in this perovskite structure and making it bismuth, which has a large 6s electron contribution, so you get a very large polarization from that. And you can put the magnetism into the B site, in this case iron. Typically, these are super exchange coupled, therefore they're antiferromagnetic. Okay. And that's a big question that we're going to deal with. You could also have geometrically driven systems like yttrium manganite, charge ordering, which was very controversial. People don't believe it anymore, actually. These are the Spinel type systems. I'm going to talk about this at the end of my talk today, so let's postpone this. Where I can go in and, with MBE-like techniques, I can essentially atomically design coupling. How does one go about doing it is what we will talk at the end. Okay, this material is an amazing material. It seems like it has so many facets. It's very much like, again, I like to look at simple analogies, very much like a Bollywood movie. You know, Bollywood movies are fantastic business propositions because they provide something for everybody. You know, the good Bollywood movies, they have the crying sequences, the dancing sequences, the fighting sequences. So the entire demographics is covered. This material has behavior very similar to that, in the sense that it has a lot of different nuances to it. It's a very good example of correlations, because if you did not include the correlations, the interactions between the iron, the material is actually a metal. And clearly it's not, it's an insulator, a band gap of about 2.7 eV. The ferroelectric polarization, by far one of the highest, it's about 90 microcoulombs per centimeter squared, pointing along the 111 axis, which is this axis, and with a TC of about 830 degrees centigrade. I told you a few minutes ago that this has super exchange interactions between the iron. That's shown here. It's got this G-type antiferromagnet. In very simple terms, you have 111 planes of the perovskite structure, which are antiferromagnetically coupled to each other. Now, if that's all that happened, this would be a little bit boring material. Actually, it would not be useful at all for us. It turns out that because of something called the Dzyaloshinski-Moriya coupling, an antisymmetric coupling, you have a very small Canton moment of the order of about 8 EMU per cc. Now, if this moment had been 50 EMU per cc, which is very difficult to do with just Dzyaloshinski-Moriya coupling, if it had been 50, this material would already be in technology. Unfortunately, 8 is just a little bit too small to be useful. Therefore, you have to do some materials manipulations to get to something that's technologically useful. Okay, so this is perhaps 80% of the entire field of multiferroics. There have been about 20,000 papers still going, people still publishing papers, including myself, and we, in some sense, published one of the early papers. I went away to do my tour of duty in Washington and came back and realized a lot of questions still unanswered, and you'll see some of them today. Okay, I'm going to skip this. This just tells you about our deposition process. Basically, we now have the ability to grow materials with atomic scale precision. And this is just an example of this material. There are 6 unit cells of bismuth iron oxide here, and you can basically follow them one atom at a time. You can put down these things either by regular MBE systems or by laser MBE and grow them with 2 angstrom precision. That's half of the unit cell of the perovskite structure. And that's basically what this TEM shows you. You can get it on a large enough scale to start to do measurements. In about 10 minutes, we're going to get to, hey, what can I do at the scale of a nanometer? That's the state of the art in some sense for this field. The first question we asked, which was a very controversial question, was if I switch my polarization, that's a white arrow, by 71 degrees, 109 degrees, or 180 degrees, those are the symmetry operators for the rhombohedral crystal structure. So rotate my polarization from this to this, from this to this, and from this by 180. The question was, what happens to the antiferromagnetism? What happens to that Canton moment? And this was controversial because Nikola wrote a paper about 10, 12 years ago which said, look, if I have this as my antiferromagnetic plane, the polarization vector is pointing out, so it's a classical right-hand rule. P, L, and M form the right-hand screw. So if I switch my P by 180, she said nothing should happen to the magnetism. It remains where it is. About the same time, we were seeing data in some of our measurements where clearly we were seeing indications that the magnetism was changing. And so we used to have fierce battles amongst us, in this case, fighting with theorists and saying, we don't understand what you're talking about. Okay, I'm going to show you data and a different ab initio calculation which said, yeah, there is a pathway to take care of this. And so the first experiment, this is now about 12, 13 years ago, was where we did a combination of two different experiments. We looked at the ferroelectric structure using piezo force microscopy, simply coming to the surface, and you put an AC signal on the surface, and the crystal would do the same. It'll be in resonance with the amplitude of the cantilever, and so you can map out the piezoelectric response with a resolution of about 20, 30 nanometers. Okay. That's what this is, and this is bismuth ferrite. I can take exactly the same region by putting markers and put it into a photoemission electron microscope and use linearly polarized X-rays and ask the question, what happens? And what you see is an image that looks kind of very similar to this. And in this particular case, depending on how you image, we use the iron absorption edge to do the imaging. Depending on whether you use the L2 or the L3 edge, you get some complementary information. But it basically maps out a combination of ferroelectric polarization and antiferromagnetism. Conversely, if you had a ferromagnetic layer, you could use circularly polarized light, and you can map out ferromagnetism. Then what we did was took the same sample and applied an electric field to a small area and switched it by various different mechanisms. And we said, what happens to the antiferromagnetism? And what we found was that indeed the antiferromagnetism has changed, which is here, in response to the ferroelectric polarization, which had also changed. And so we mapped it out. We said, hey, look, when you switch the ferroelectric polarization, it looks like the antiferromagnetism is also changing. This was way back in 2006. And I don't think we really understood all of this very well. I don't think we do even now, but we have a lot better field today than we did in 2006. A few years afterwards, we were doing an experiment which came out in this Nature paper where we were saying, if I switch the ferroelectric polarization for bismuth ferrite, how does this switch? And this is a set of experiments which is actually still baffling, and I'll tell you why it's baffling. What these are ferroelectric domains. Think of domains which are rotated by 71 degrees. So these look like the slats on the surface here. They're rotated by 71 degrees from each other. So the greens and the blues have a 71-degree rotation in the polarization. You can then apply an electric field and map out with time resolution of the order of microseconds what happens to the polarization. And what we found was that essentially they go from like this to like this. Each one of the domains rotates by 180, but the neighboring one is 71 degrees apart. Okay. But what was fascinating was that for each of the domains, that rotation process happened in 2 steps. And at that point, nobody had really described the switching of a ferroelectric in a 2-step process. Okay. So in this particular case, the ferroelectric was behaving more like a ferromagnet. In a ferromagnet, you're dominated by exchange interaction, and therefore, you're simply rotating the polarization, also the magnetization, through a block wall or a nail wall, but the magnitude of the moment does not dramatically change. In contrast, the conventional wisdom for a ferroelectric was that the dipole moment would continuously change. The dipole moment was never thought to be a fundamental quantity. It's a mutable quantity. So it was big on one side, slowly decreased, and then flipped over to the other side. Okay. Instead, bismuth ferrite was telling us that it didn't do that. It actually rotated this way and did a second switch. And so we're still saying, that is very strange, and we don't understand it, which is why I put a question mark. Why does bismuth ferrite behave like a ferromagnet? Okay. Then if you map out for this region, it turns out that a significant, maybe 80–85% of the material switched in a two-step process. And it turns out that was very important because that could give us a pathway by which we could question Nikola's theory. And Jorge did that. What Jorge did was to do ab initio calculation, but his primary claim was, hey, look, when they did the first set of calculations, they did not look at all the ground states. And he said if they had looked at all the ground states, they would have seen other pathways. And indeed, that is true. So what he did was to do the 71, 109, or the 180 coming up, but he said, I'm going to let the X, Y, and Z components of the polarization and the structural distortions all float. So for example, if you do the energy versus the position, for the 71-degree switch, the bismuth ion shift, which is mainly mapping the polarization, it was changing along the X or the Z. X and Y did not change. The octahedral rotation, which maps the magnetism of the system, or the Canton moment, was changing along the Z, did not change along X and Y, so on and so forth. We'll go to the main conclusion. What Jorge concluded was that when you do a 180 switch by a single process, it didn't like it very much. In this case, he said it went through these 3 steps, and actually it goes through 2 steps. One, a 71-degree rotation, followed by another 109-degree rotation, adding up to 180. In this case, the Canton moment also rotates by 180. That was very consistent with a lot of our experimental data, which is shown in this slide. This was this paper that we wrote in 2014. I actually didn't think much about this because I was doing other things. I was still coming back from the Washington work. It turns out this paper caught the Intel people, and they latched onto it. And so the work that we're doing with them now is all based on this work. Let me take you through what this slide is telling you. Okay? On the top left, you have the ferroelectric domains. Those are the stripy things we talked about. Those are 71-degree rotated domains. The corresponding magnetic domains of a ferromagnet, in this case a piece of cobalt iron, is shown here in this image. Again, it's a photoemission electron microscope image using circularly polarized light, which is sensitive to ferromagnetism. Okay. You could see these two guys look exactly the same. So the first thing that the postdoc concluded was, oh, look, the ferroelectricity is controlling the magnetism. Absolutely not. They don't talk to each other. It turns out that the Canton moment in the bismuth ferrite is mapping exactly the same way in these domains, and so it was just accidental. So the ferromagnet, the cobalt iron, was coupling to the Canton moment. Okay? That turns out it is like the small player in the entire movie, but that small player is the most important player to make the movie work. So we did a whole bunch of things. I'm going to show you 2 pieces of data. This is a spin valve that we made, which is just a ferromagnet, metal ferromagnet layer, and put it on the bismuth iron oxide. And we switched it electrically. And the red data is a ferroelectric switching data, meaning I'm switching the polarization order. And the blue data is the spin valve resistance. What you take away from this is that as I'm switching the polarization order, the spin valve is also switching. I'm going to show you a little bit more of this in the next couple of slides. Okay. So what it's telling you is that if I apply of the order of 6–8 volts, I could switch my ferroelectric, and I could also switch my ferromagnet by switching the spin valve. You could go back and image that by using photoemission microscopy. This is a small island of the ferromagnet. These are the metal pads, and you can do it before poling, and after a single pulse, it goes from white to black, meaning that the magnetization has switched by 180 degrees. And so we went back, did other measurements, ferromagnetic resonance measurements, to truly prove to ourselves that we are switching the direction of the magnetization by 180 degrees by switching the polarization by 180. Okay? That's shown here schematically. Here, it's a little bit more of complex arrows going back and forth, but trust me, it's telling you that the canted movement in the bismuth ferrite is doing from this to this, and the ferromagnet is doing the same because they're coupled to each other. They're exchange coupled to each other. Okay. Oh, this is going too fast. After that paper, we were kind of quiet. We were doing other things. Intel picked up on this whole idea. And they said, hey, look, we want to start to fund you guys. And indeed, they have kind of started picking up quite a bit. The first thing that Sashi did was to go look at very small structures by E-beam lithography, which we could not do at Berkeley. And so he measured the GMR hysteresis loops. This is just standard GMR measurement. And these are the calculations, micromagnetic calculations for a 2-micron device versus a 200 nanometer device. What he found was that the coupling became stronger as I reduced the lateral dimension. That was the first. The second thing that he found was the coupling became very directional, not axial. There was an exchange bias coupling between the spin valve and the multiferroic. That's shown here by this red box. It's telling you that this does not exist for the larger devices, but it starts to happen for the smaller devices. And the calculations actually agree with that, with the experimental data. So we were seeing something which we had never seen in our previous Nature paper. So that's now, Sashi has submitted it to some journal for publication, that there's a strong exchange bias. For a device that we're going to chat about in a minute, this exchange bias happens to be very important. Okay, and so what he also showed, this beautiful measurements from his side, is that you have bidirectional switching of the magnetization in the spin valve, very consistent with Jorge's theory. The electric field out of plane produces an effective internal bias to the left and vice versa to the right. And you can see that the red curve and the green curve, the pristine data is here, are flipping directions as I go with -5 and +4. Okay. So by now, I hope you have gotten this one message which says, hey, at 8 volts, I can switch my magnetization direction by 180 degrees by applying an electric field. Okay? So that's a first level summary. We did some faster measurements. This is just data showing you that we can do it at a few microseconds, maybe 10, 20 microseconds. And ideally, you can go at the acoustic phonon mode. The switching speed for ferroelectrics is controlled by the acoustic phonon mode, typically the velocity of sound. So we think we can go at maybe nanosecond or faster, no problems. Okay, now comes the killer part of it, which is making me sweat. I have never worked this hard in my life. I'll tell you why. So Intel said, guys, this is very nice. We have a proposal for a brand new logic device, and it's called the MESO device, Magneto-Electric Spin Orbit Coupled Device. I was not going to go through the full circuit calculations, which I have, but this becomes a totally different talk. But this device looks very different than the CMOS device, and it's based on the spin of the electron. It has two components to it. The first part of it is a conversion from spin to charge using the inverse Rashba effect, or the inverse spin Hall effect. And that's one module of this device. Then there's a metal connector, and then you have charge to spin, which is accomplished by magneto-electric switching. All very nice, except Intel said, hey, we need to do this at 100 millivolts. Okay. Now, 100 millivolts is important because it approximately translates to an attojoule per logic operation. 6 orders of magnitude smaller than what today's CMOS has. Okay. We said, oh, that's very interesting, very difficult. Okay. So I'm going to try to take you through how we're beginning to think about this problem. I will not tell you that we have the answers to this. I will tell you that this is perhaps one of the most exciting games I've played in this business. I've been in looking at these oxides for about 25 years, 30 years now. It's very challenging. Getting to 100 millivolts, nobody in the ferroelectrics business has tried it before. Okay. I'm also going to give you some metrics in a second. So the pathways to an attojoule magnetoelectric component. What do we need to do? We need to reduce the switch polarization. You don't want a large polarization. A large polarization is like carrying a big bag with you. You don't want a big bag. You need a small bag with a few vegetables. That's all you care. Okay. You want very low coercive voltages. You don't want to be going through a huge energy barrier, and we're going to talk about that in a second. You want very large magnetoelectric coupling. Of course, you go to very small device dimensions. And our fundamental assumption is that we will get to a 10 by 10 nanometer, which is kind of the state of the art for today's CMOS. You know, people say 7 nanometers, but really everybody's working at about 10 to 12 nanometers CMOS. Okay. So a lot of questions. How stable is this? What is the nature of the coupling at interfaces? Do I need an oxide ferromagnet? I think we do. How does a metallic ferromagnet couple to an oxide? All of these questions have to be answered. On the other side, the challenges are even more tougher. That's why when I was talking to some folks this morning about bismuth selenide, bismuth telluride, materials which have very large spin-orbit coupling, if you think there is some fantastic challenges, here's one of them. Okay? This is just our standard inverse Rashba device. Basically, we have permalloy as a ferromagnet and a material with large spin-orbit coupling. And the experiment is basically to measure this spin-Hall angle, which translates to the spin-Hall voltage, okay, which typically today is of the order of microvolts, maybe 50 microvolts. We need to get to 100 millivolts, several orders of magnitude larger values of the spin-Hall voltage. How does one go about doing this? You clearly need materials with large spin-orbit coupling, but is there a role for correlated materials there? So in my group, we're going back to oxides. We're looking at manganites. We're looking at highly correlated with large spin polarization, oxide ferromagnets, with materials like the ruthenides and the iridates, which have large spin orbit coupling, as a way to get large inverse spin Hall effects. This is by no means an easy problem to solve. I don't think anybody has a good fix on this. So this is a fantastic opportunity for graduate students to get in. The one thing nice about this is Sashi's calculation, is that it goes as a cube of the lateral dimensions. So as I make the devices smaller and smaller, and indeed our data does show that as you make them smaller and smaller, the inverse spin Hall voltage goes up as a cube of the dimension. Okay, now coming back to magnetoelectrics. I'm sure you've seen this in textbooks. This is just the standard double well structure for a ferroelectric given by this classical Landau type approach. So you can now say, if I have to reduce the energy required to go from this part to this part, I need to tune this. I need to start to tune all of the Landau parameters. Can I change the composition? Can I change thickness? What are my variables that I can use? What is the role of structural distortions, for example, on switching? All of these are open questions. Now, in ferroelectrics, there is a well-studied approach called the K-Dunn scaling law, where the coercive field goes as T being the thickness, power minus 2/3. That's a problem. And that's shown here with data from a really nice paper that Peter Littlewood, who you guys know very well, Peter and Jim Scott and a bunch of people wrote. Over a very large range of thickness, it seems to follow this. It was something published in the late 50s, early 60s. And that's a problem because then you are sublinear, and therefore reducing my thickness is okay, but it's not the best way to do it. So the physics of this is completely open question. Nobody really understands well enough. Okay, what we've been doing over the last year or so is to understand how the order parameter changes, how the switching of the ferroelectric crystal changes as I reduce dimensions. This is work we did a few years ago, actually, using piezo force microscopy. We know that even 2 unit cells of bismuth iron oxide is a good ferroelectric. It is not the same ferroelectric. It suppresses its order parameter quite a bit, but it's definitely switching. Okay. You could also see some signatures of why the coercive field is not dropping as 1 by T. It's sublinear. Over the last year or so, we've been working with some folks at Connecticut. Brian Huey is a faculty member there, where you can take an atomic force microscope, and you can, it's very much like shaving with the atomic force microscope. You cut one layer after the other, and that's this called tomographic AFM. So you can take a 100 nanometer thick sample, and you can progressively reduce the thickness and measure the ferroelectric properties. That's what Brian did. And indeed, the coercive field for the same sample looks like this. Let me show it to you in a little bit different way. This is plotting the coercive field versus thickness, and you can see that's the data. It does indeed go as minus 2/3, so it is very well fitting to the prior data. But you could also see that these are AFM-based measurements. These are measurements of the same bismuth iron oxide composition, but by using a capacitor structure, which means my contact electrodes are very important. And therefore, interfaces play a big role in how the switching happens. I've also plotted here the triangle where I need to get to. That's my Bermuda Triangle. That's where I get 100 millivolts of switching. You can see there's one red data, which I'm going to get to in the next slide. This is where I need to be. And you can see we're not there yet. Okay. Let me get to the red data in the next slide. Over the last year, as I said, we've been looking at how do I reduce the thickness? How do I play games with the chemical structure? And in this case, we take bismuth iron oxide and dilute it. Now, it's very much like take your favorite drink and putting water into it, and you dilute it. Here we dilute the polarization by substituting lanthanum into the bismuth site. And indeed, the polarization comes down. Indeed, the structural distortion comes down. These are quasi-static piezoelectric measurements. And you can see that the polarization is switching, and the switching voltage is about 150 millivolts. This is still the state-of-the-art record for the switching of these ferroelectrics. We're still trying to understand the details. When I do this measurement in a dynamic fashion, meaning in a pulsing mode, it is much larger. It's about 400, 500 millivolts. But that's the state of the art. We need to go long ways from there to figure out how this works. Okay, we can do this with high speeds. We know how to do very fast switching, go down to maybe tens of nanoseconds. We know that the ferroelectric will switch, which doesn't really give us much trouble. I want to show you two really new pieces of data. I'm very happy about this because it took us a lot of effort to get to this. So basically, you could see we have now built spin valves on a 45 nanometer multiferroic. That's the nice GMR hysteresis loop. This is exactly what it should look like, textbook almost. That's basically the resistance GMR versus magnetic field. But what you can see is with 2.5 volts, it shifts significantly between the red and the green, telling you that I have now changed the magnetization direction with just 2.5 volts. So we've gone from 8 volts, 5 volts, now to 2.5 volts. And the switching actually happens around 1 volt. Okay? And you can see all of that summarized here. The phase of the piezoelectric switching and the resistance are all matching up around 1 volt. If I go by another 50% down in thickness, this is 23 nanometers, that voltage goes down to 0.5 volt. So we're in the process of looking at 10 nanometers and 5 nanometers of the multiferroic. The question is, what happens to the coupling? Are these materials the same as a macroscopic material, or is it very different? And we're still trying to probe that. One of the ways to probe it is to directly image the order parameters. Here's the case of 2 nanometers, 5 unit cells of the multiferroic. That's bismuth iron oxide. Is 1, 2, 3, 4, 5. 5 unit cells. Okay. These are atomic resolution images. With these images, you can not only get the atomic positions, you can also get the relative displacements. And what you can see from this is that this is the strontium ruthenate layer, this is a metal, is that the dipoles in the bismuth iron oxide are all pointing towards the bottom electrode, which is exactly what it should do. But it also says that there is nowhere in the sample where the dipoles are pointing up. So we don't know if a 2 nanometer layer is ferroelectric or simply has broken inversion symmetry. And so we're now getting into trying to understand how does one switch a 2 nanometer thick layer of these kinds of materials, which is where we need to be to reduce the voltages significantly. Okay. What we also know is that there is strong linear dichroism, which means it's still antiferromagnetic. We know that for sure. We know that it couples to a ferromagnet reasonably well. What we don't know is how do these magnetoelectric coupling work at these kinds of dimensions. Okay, so in our march towards 100 millivolts, we started here somewhere in a few years ago. We're somewhere out here. And we need to go to this hallowed land of the green star. Lot of questions still unanswered. Most of them are physics-based questions. Okay? Do we need to come very close to a phase instability? And it's something I've been pondering. We want to put the system, it's very much like human beings. You want, they're most productive when at the edge of a phase transition. If everything is very flat, you're not very productive. You need to be edgy. I think we want to do the same thing with the multiferroic, getting close to a phase instability. Of course, tune the polarization, pay attention to interfaces. How does charge transfer across the interfaces? We need to understand them much better. And look at antiferroelectric phases, for example. Then we said, hey, is it possible that I can go one step more in resolution and start to look at atomically designing these things? That brings me to the last couple of slides in my presentation. This is a beautiful piece of work. One of my postdocs, who's now a big professor at Harvard, Julia Mundy, did her PhD with Darrell Schlom at Cornell, and she was a scholar with us for 2 to 3 years. So the idea was the following. Right? If you look at this compound, lutetium iron oxide spinel, it's not a spinel, it has a related structure. It is very magnetic with a TC of about 240 Kelvin. It's nonpolar. There was a lot of debate about 10 years ago whether it was a polar compound or a nonpolar compound. Now everybody is agreed that it's nonpolar. If you look at its sister compound, 113 compound, that is a canted antiferromagnet with a TC of about 140 Kelvin, but it's a very good ferroelectric. It's a TC of about 1,000 Kelvin. The polarization is very small. Now, these two guys are atomic resolution images, and you can clearly see where the polarization is going to come from. You can see the 2 lutetiums up, 1 down. So it has a 2 up, 1 down, 2 up, 1 down, structural distortion. So lutetium iron oxide 113 is called an improper ferroelectric, meaning the primary order parameter is not a charge degree of freedom, but a structural degree of freedom. And that structural degree of freedom couples to the charge, and the charge becomes a slave in some sense. So our thinking in this work, which got published in Nature a year or so ago, was to take this ferrimagnetic phase and couple it to the ferroelectric phase and create a multiferroid where the coupling is through the puckering of these things, puckering of the 2 up and 1 down kind of layers. And indeed, that happens. I'm going to quickly show you the data before we finish up. We talked about the puckering. That's the puckering, the 2 up, 1 down, 2 up, 1 down. That delta that you see there is the distortion that relates to the polarization. Okay. So now you have a way by which you can microscopically, at the atomic scale, design in coupling between the magnetic degree of freedom and the charge degree of freedom. So indeed, we synthesized it. That's the paper I was talking about. We can tune the thicknesses of the various layers. We can go from pure lutetium-113 to lutetium-124. And it's essentially building your sandwich the way you want to make it. Okay. And so these are the various sequences all the way from the pure phases to the various layering shown by this stuff. And indeed, by the time you hit this part, where m equals 9 is our favorite composition, we saw some very strong enhancements of the moment, and we believe that's because of the puckering. So we can also go back and design in the ferroelectricity, but that wasn't that big a deal because the parent compound was already a good ferroelectric. And we have done a lot of measurements using dichroism, and indeed we can tune the ferroelectric transition by using various layering sequences. But here's the most interesting measurement that we did, not in this picture, in the next slide. We can write ferroelectric patterns. The reds and the blues are simply polarization vectors pointing up and down. They're very stable over months now. This was done almost a year ago. But you can take that pattern now and then go and ask the question, hey, tell me what happens to the magnetic degree of freedom. Right? I have switched the ferroelectric, the charge degree of freedom, from up to down. I can go back to the photoemission microscope and do circular dichroism measurement of the magnetic degree of freedom. That's what this data is. What it's telling you is that, indeed, the magnetic degree of freedom at 200 Kelvin, albeit, is switching in response to the polarization degree of freedom going up and down. And it goes away by the time you hit about 300, 320, because the Curie temperature of the ferrimagnet is about room temperature, 300 Kelvin. So it tells you that indeed this notion is doable. So we are now completely immersed in trying to create such artificial superlattices where I can design in the magnetic compound and the ferroelectric compound and couple them with the lattice as the degree of freedom. Okay. That brings me to the summary. I hope you have taken a few messages away. By far, for the students in the audience, by far the most important thing is I still get a big high doing science. It's a lot of fun. I took a few years sabbatical when I did my tour of duty in Washington. That was a lot of fun too. I worked with Steve Chu, Nobel laureate, amazing guy to work for, deep convictions about climate change and everything. But, and I actually was going to chicken out in 2013. I went to Oak Ridge National Lab to be their deputy lab director, thinking I'm done with science, I'm going to be a manager. What I did not realize is that my science community, I figured, who's going to notice if some monkey like Ramesh walks away from science? Bad idea. A whole bunch of people said, that was the stupidest thing you've done. You know, Professor Faird, who is a big sensei, Nobel laureate, he said, Ramesh, why do you have to do all this management stuff? Go back to science. Bob Dines, who of course is a very big guy, president of the UC at that time, he said, yeah, maybe you should be doing science. You know, a whole bunch of people said, go back to science. And I said, okay, I will. You know. That's the best advice I've gotten from people. It is a lot of fun to do science. I mean, but of course, I'm not 25, I'm not 35, I'm not even 45. Actually, I'm not even 55 anymore. So I know time is finite. That infinite axis has become shrunk. I feel a sense of urgency. I gave a talk at Trichy at the NIT. We need to have a sense of urgency. Climate change does not wait. CO2 is going up as we speak. This project just happens to be another kind of manifestation of the sense of urgency. So I try to work as though there is no tomorrow. So today is the only day you're guaranteed. I did want to convey to the students and my colleagues here the excitement of doing the science. You know, I mean, we publish a lot of papers and stuff, but even now, when you get a paper accepted in Science or Nature, it's like, yeah, that's great, you know. And so we go out and celebrate and all the other stuff. I hope I've given you a reasonable feel for this interesting problem. And for me, getting Intel involved has been amazing. When Intel comes and tells you, guys, we have a problem, we need to do something different, you sit and pay attention. Because this company is we don't need you guys, you professors are a waste of time. That's their attitude. But no, it's exactly the opposite. So much so that it's on a religious basis every day. Even now I Skype back and forth with my colleagues at Intel. We spend a lot of time going through how does one solve this problem. Both sides of this new device, whether the spin-orbit coupling or the magnetoelectric, getting to 100 millivolts, those are fantastic targets. If you can hit them, they are worthy of something very special. Okay. How to do it requires the physics. So the physics community, the materials community, the measurement community, all of them have to be in it. Okay. The fact that Intel is jumping into it says that if we're able to, sorry, I shouldn't say if, when we're able to solve these problems, there is a haloed land, there is a light, a big piece of light at the end of the tunnel. I hope I've conveyed that message. I hope I've shown you that indeed it is possible, that we have now come down from 5 volts to about 500 millivolts. 500 millivolts to 100 millivolts is going to be big lift. So you need a lot of new science. And so I showed you some data on the physics of scaling. We still don't understand these materials at the scale of the unit cell. Much of it is still macroscopic. So we need probes. We need a lot more new techniques to measure these things with microscopic resolution. Okay. But the field, very clearly, I mean, I can see it now. I took a sabbatical and came back. The field is in a very interesting juncture. And so I kind of feel privileged to be able to come back and start to work on it. So please stay tuned, and thank you so much for the opportunity. I grew up in Calcutta, many years ago, so it's always very special to come back to the city. Thank you once again to Sudhakar and to the director for the chance to come and give this talk. We can take questions. Yes, sir. Yeah. Awesome questions, both really awesome questions. I'm very optimistic. Perhaps I'm hyper optimistic, but if free of cost, right? I don't have to pay money to be optimistic, so I can do it. But here's the point. when we started working in 1989 on ferroelectric memories, the silicon people said, oh, we can't deal with these oxides. These are dirty materials. People figured out a way to do back-end processing. So you can go to a standard CMOS fab and do, after metal one, you can go back and put your oxides, do all the stuff, and there are pathways. Now, Panasonic is making some money. Samsung, Fujitsu are all in it making ferroelectric memories. So I think it's possible. The question, your question is loaded, absolutely well taken. Since, do you need epitaxial materials? And maybe we do. And we have pathways to do that. We can grow epitaxial oxides on silicon. Now, this is what Daryl and I pioneered for about 20 years, and I think we have pathways to do it. So yeah, I think it is quite reasonable. To me, the biggest positive indicator is that Intel is telling me that, hey, we can do it. No, I said, dude, are you sure? You want to put these crazy complex materials? Yeah, don't worry about it. No, and it's not that there's this crazy Indian fellow who's talking there. I've talked to the managers. They're all saying, yeah, we need a different solution to standard CMOS. Ask me your second question again. I kind of. Yes. Yeah, right. So I think that's a really good question. I can define for you what the attributes of that system should like. It should look like Shah Rukh Khan, have nice dancing sequences, blah, blah, blah. But beyond that, Amir Khan is good too, And so now translate that back to multiferroics. I think bismuth ferrite is good because it's the only system which has the ordering parameters at high enough temperatures. So it's a robust material. So you got to be room temperature. So that's no question. So that's one reason. There are some negatives with that system because it distorts very strongly. I think we can tune it. I don't think we have tapped the limits of coupling mechanisms. And so those artificial superlattices may be a pathway to get to much more effective coupling mechanisms. The one big issue with the bismuth ferrite is we're now using a metallic ferromagnet. Those interfaces always Schottky barriers. Schottky barriers means you're losing some taxes, and so you don't want to do that. So we're kind of desperately looking for oxide ferromagnets which are robust at room temperature and stuff like that. So. Students, it's really important to have arguments. I cannot tell you how important it is to have a fight, whether it's with a speaker, your faculty. I also keep saying this to my students. At least a third of the time, you have to say the professor is an idiot, I'm going to prove him wrong. Okay? You have to go with that conviction. And my job is to keep pushing that student to say, how do you keep doing that? Develop the conviction to say, I'm going to prove the professor wrong. That's how you become the genius. That's how you become published at Science or Nature paper. Really important. So it's very important to engage in this process. For sure. Like I was giving you this example of the lutetium ferrite, lattice coupling is important. So the big message in all of this is the lattice plays a big role, because I don't think you can do this just with quantum mechanics, right? So the lattice is important. Having said that, heterostructures give you a way to control things with atomic precision, control what you put on top of something else. And so, yeah, those things are going to be, we already have maybe 5 different variants of that idea. As a matter of fact, there's another piece of data which I didn't talk about because, it's a paper that's just being submitted to Nature where there are totally new materials coming up, where you can go back and play chemistry games with this system. So I think that's going to be pretty interesting for the next 5 years. Yes, sir. Right. 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 Yeah. Yeah. Well, I think that's a good point. It depends on what you look for. If you look at bismuth ferrite, the spontaneous polarization is essentially the bulk. Actually, the thin films from our group was the first time that we got the bulk number. The bulk ceramic ones were totally goofy. Having said that, if I reduce my dimension from, say, 100 nanometers to 1 nanometer, my order parameters change dramatically. The polarization has been suppressed by 90%. So it's no more the same material. But with the thin film heterostructure approach, you really need to be more accepting. You've got to basically have Hinduism as your basis. You have to accept many different manifestations of the material and see, what do I do to understand it? What do I do to use it? Yes, sir. Mm-hmm. Yeah, so if you look at the early portion of my presentation, we used, perhaps I didn't explain it well enough, which is why you're asking this question. The antiferromagnet, ferroelectric is at the bottom. Then you have a layer of a ferromagnet which is coupling magnetically to that. And so think of it as, again, simple analogy like doing old-fashioned photography, not iPhone photography, but the Kodak version. You take a negative, put a positive, and the peel off, and the positive is the one that you take away. That's pretty much what it does. The ferromagnet on top basically mimics the underlying antiferromagnet or the Canton moment. Exchange couple, that's right. Yeah. Okay, thank you very much.